For as long as we have been human, we have gazed at the night sky in wonder, searching for our place among the silent, glittering points of light. Welcome to the Restful Stories. We love to explore these grand narratives of science and the universe. And if you find you enjoy this journey as well, we invite you to subscribe to the channel so you won't miss any of our future stories. Tonight, we journey through a landscape we think we know, the familiar celestial neighborhood we call home. But this is no simple tour of static, distant worlds. It is a story of cosmic violence and delicate beauty, of fiery birth and frozen, silent endings. It is the biography of our sun and the diverse family of worlds that it commands, a story written in the language of gravity and light, of time and chemistry. And like all great stories, this one has a beginning, a moment of creation deep in the cosmic past, long before our world, or even our star, had taken shape. Our story begins in the unfathomable depths of time, in a swirling cloud of gas and dust left over from the birth of stars. Here, in a quiet arm of a vast spiral galaxy, a cosmic drama was set to unfold. From this primordial nebula, our solar system ignited, a process that began some 4.6 billion years ago. For a sense of scale, our own species has walked the Earth for a mere fraction of 1% of that time. This cosmic home of ours is now in its comfortable middle age, a stable and predictable system. And scientists estimate it will continue much as it is for another 5 billion years, a future timescale as immense and difficult to grasp as its past. The central character in this story, the anchor of our existence, is of course our star, the sun. It is a celestial titan of such immense proportions that it accounts for 99.86% of all the matter in the entire solar system. Everything else, every planet, moon, asteroid, and comet, is collectively just a rounding error in the sun's cosmic ledger. This overwhelming dominance of mass translates into an unshakable gravitational authority. The sun does not merely sit at the center of our system. It commands it. Its gravity is the invisible hand that sculpted the orbits of the planets, that holds them in their perpetual dance, and that dictates the fate of every object caught in its embrace. All the worlds we know, including our own, are bound to this star, forever circling in a testament to its singular power. From the fiery heart of this stellar behemoth, light begins an incredible journey. Each photon, a tiny particle of energy, travels outwards, first through the dense plasma of the sun's interior, and then erupting from its surface to cross the void of space. To reach our world, this light travels for about 8 minutes and 20 seconds, covering a distance of nearly 150 million kilometers, or about 93 million miles. This means that when you look at the sun in the sky, you are seeing it not as it is now, but as it was over 8 minutes ago. There is always a delay in our cosmic conversation. Yet, this swift journey to Earth is but a short sprint in the marathon of light's voyage through the solar system. To travel from the sun to the very edge of its influence, beyond the orbit of the farthest planet, and out to the boundary where the solar wind gives way to interstellar space, a single photon of sunlight must travel for more than a year. This vast, sun-drenched bubble, known as the heliosphere, defines the true scale of our cosmic home, a kingdom of light that takes an astonishing amount of time to cross. Within this kingdom reside the 8 planets, each a unique world with its own story. In order of their distance from the Sun, they are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. This family of worlds is a diverse collection, from small, rocky bodies to colossal giants of gas and ice. Their identities are deeply woven into the fabric of human history, a connection reflected in their names. With few exceptions, these celestial bodies were named by ancient astronomers in honor of the gods and goddesses of Roman mythology. Jupiter, the colossal king of the planets, is named for the king of the gods. Mars, the world of crimson rock, bears the name of the god of war. Venus, the brilliant beacon of the morning and evening sky, is named for the goddess of love and beauty. This tradition was broken only once among the major planets, with the discovery of Uranus in the 18th century by the astronomer William Herschel. Instead of a Roman deity, it was given the name of a much older figure from Greek mythology, Ouranos, the primordial god of the sky. The one name that stands apart from all this divine nomenclature is, of course, our own. The name Earth does not come from a grand celestial myth, but from something far more humble and immediate. It is a word rooted in the Old English and German languages, derived from terms like Eortha and Erd, which simply mean the ground, the soil, the dust beneath our feet. Our planet's name, at least 1,000 years old, is a constant reminder of our terrestrial origins, our deep connection to the land itself. Our journey through the planets begins with the inner worlds, where conditions are extreme. Here we find a cosmic riddle in the relationship between Mercury and Venus. While Mercury is the closest planet to the Sun, orbiting in its scorching glare, it is not the hottest world in our solar system. That fiery distinction belongs to its neighbor, Venus. The second planet from the Sun is a true inferno, a world where the average surface temperature is a staggering 475 degrees Celsius, a searing 875 degrees Fahrenheit. This is hot enough to melt lead. The reason for this intense heat is not proximity to the Sun, but a thick, toxic atmosphere. Venus is shrouded in a dense blanket of carbon dioxide and clouds of sulfuric acid, creating a runaway greenhouse effect that traps heat with terrifying efficiency. This atmosphere is so heavy that the pressure on the surface is over 90 times that of Earth's, equivalent to the crushing pressure found nearly a kilometer, or well over half a mile, deep in our oceans. Venus is a world of extremes in more ways than one, a place where time itself seems to move at a different pace. It possesses one of the most peculiar rotations of any planet. A single day on Venus, the time it takes to complete one rotation on its axis, lasts for 243 Earth days. In a bizarre twist of celestial mechanics, its journey around the sun, its year, is shorter, taking only 225 Earth days to complete. This means that on Venus, a day is longer than a year, a concept that fundamentally challenges our earthly understanding of time's passage. The sun rises and sets on an impossibly slow schedule, painting a sky that is both alien and utterly hostile. This hostility is not just atmospheric. It is written into the very motion of the planet itself. As if to defy the celestial norm, Venus is the only planet to spin on its axis in a clockwise direction. All other planets, with the exception of the oddly tilted Uranus, follow a counterclockwise or prograde rotation. Venus's retrograde motion is a profound anomaly, a cosmic rebellion that sets it apart. It means that on Venus, the sun would appear to rise in the west and set in the east, a daily spectacle that unfolds over a period longer than the planet's entire year. The reasons for this backward spin are still a matter of scientific debate, with leading theories suggesting a colossal impact in its distant past that literally knocked the planet upside down, or perhaps the long-term effects of its incredibly thick atmosphere dragging on the surface and reversing its original spin. Whatever the cause, this unique rotation is another mark of the planet's profoundly alien nature, a world of fissure, pressure, and backward days. Moving away from this inhospitable furnace, we find ourselves approaching a world of breathtaking contrast, a shimmering blue and white marble suspended in the blackness. This is our home, the Earth, and its most profound distinction is a simple yet miraculous one. It is the only planet in our solar system known to support life. From the deepest oceanic trenches to the highest mountain peaks, life has found a way to thrive, creating a complex and interconnected biosphere of staggering diversity. This planet is not just a rock orbiting a star. It is a living, breathing system, a rare and precious jewel in the cosmic expanse. What makes this possible is a delicate confluence of factors, a series of fortunate circumstances that have allowed life to take hold and flourish. A key ingredient in this recipe for life is the overwhelming presence of water. An astonishing 71% of the Earth's surface is covered by it, forming vast oceans, winding rivers, and frozen polar caps. This abundance of liquid water, a substance essential for all known biological processes, is a feature not found on this scale anywhere else in our solar system. The oceans regulate our climate, drive our weather, and serve as the crucible where life first emerged billions of years ago. But having water is not enough. A world also needs protection. Earth possesses a powerful magnetic field, an invisible shield generated by the molten iron core deep within its interior. This magnetosphere extends far out into space, a protective bubble that deflects the most dangerous particles streaming from the sun. This constant onslaught, known as the solar wind, is a torrent of charged particles that would otherwise strip away our atmosphere, boil our oceans, and bombard the surface with deadly radiation. Our magnetic field is a silent, tireless guardian, a force that makes our world a safe harbor for life in an otherwise hostile cosmic sea. Leaving this vibrant haven behind, our journey takes us to our other celestial neighbor, the fourth planet from the Sun, Mars. For centuries, it has captured the human imagination, a world often called the Red Planet. This distinctive, rusty hue is not just a trick of the light. It is a chemical reality of the Martian surface. The soil and rocks are rich in iron oxide, the very same compound that forms Mars rust here on Earth. Mars is, in essence, a world covered in a fine layer of reddish dust, a global patina of age and oxidation that tells a story of a planet with a very different history than our own. While it may appear as a desolate, dusty wasteland today, Mars is a world of superlatives, a place of geological wonders on a scale that dwarfs anything on Earth. It is home to the largest volcano ever discovered in the solar system, a colossal shield volcano named Olympus Mons. This mountain is a true giant, rising a staggering 25 kilometers, or nearly 16 miles, above the surrounding plains. To put that into perspective, it is almost 3 times the height of Mount Everest, our own planet's highest peak. Its base is so vast that it would cover an area the size of the state of Arizona. This monstrous volcano is a relic of a more geologically active past, a time when molten rock surged from beneath the Martian crust to build a structure of truly planetary proportions. As if one such feature were not enough, Mars also boasts a canyon system of equally epic scale. Valles Marineris, the Mariner Valley, is a network of interconnected canyons that stretches for over 4,000 kilometers, which is about 2,500 miles along the Martian equator. This is more than 10 times the length of Earth's Grand Canyon, and in places, it plunges to depths of 7 kilometers, or over 4 miles. This is not a scar carved by a river, but a massive tectonic crack in the planet's crust, a colossal chasm that likely formed as the planet cooled and stretched billions of years ago. Despite these dramatic and alien landscapes, Mars possesses a rhythm that feels surprisingly familiar. A Martian day, which scientists call a sol, is only slightly longer than an Earth day, lasting 24 hours and 37 minutes. This near-identical day-night cycle has made Mars a focal point in our search for extraterrestrial life, as it offers a tantalizing hint of planetary kinship. Even more astonishing is the fact that we don't necessarily have to travel to Mars to study it. Here on Earth, scientists have discovered rocks that originated on the red planet. These Martian meteorites were blasted off the surface of Mars by powerful asteroid impacts or volcanic eruptions millions of years ago. They traveled through space as tiny, frozen time capsules before eventually being caught by Earth's gravity and falling to our surface, landing in places like the deserts of Antarctica and Africa. By analyzing the gases trapped within these rocks, scientists can confirm their Martian origin, giving us a tangible piece of another world to hold and to study. Our journey through the inner, rocky worlds is now complete. We have seen the extremes of heat and pressure, the miracle of a living world, and the dusty, monumental relics of our red neighbor. Now we cross a great divide, the vast expanse of the asteroid belt, and venture into a new realm, the domain of the giants. Ahead of us looms a world so vast it defies easy comprehension, a planet that contains more mass than all the other planets combined. We have arrived at the court of the king, for Jupiter is the largest planet in the solar system. This colossal gas giant is a world of storms and chaos, a planet where weather operates on a scale that is almost impossible to imagine. Its most iconic feature, a swirling crimson eye in its southern hemisphere, is known as the Great Red Spot. This is not a mere storm. It is a persistent anticyclone, a high-pressure system so vast that the entire planet Earth could be comfortably swallowed by it. We know from historical observations, some dating back to the 17th century astronomer Giovanni Cassini, that this tempest has been raging for at least 300 years, and likely much longer. It is a storm older than many nations on our own world, a testament to the sheer power and stability of Jupiter's dynamic atmosphere. The planet's entire surface is a tapestry of such weather, with colorful bands of clouds and violent vortices driven by forces deep within its interior. Yet, for all its immense size and ancient storms, Jupiter is a world in a hurry. It spins on its axis faster than any other planet, completing a full rotation in just under 10 hours. This incredible speed creates a powerful centrifugal force, causing the planet to bulge significantly at its equator and flatten at its poles. It is not a perfect sphere, but an oblate spheroid, a shape dictated by its frantic pace. This rapid spin is the engine that drives its extreme weather, whipping its clouds into the distinct parallel bands we see, and fueling the very storms that have raged for centuries. Jupiter's influence extends far beyond its own atmosphere. Its gravitational might has shaped the very architecture of the solar system. In the vast gap between Mars and Jupiter, lies the main asteroid belt, a sprawling collection of rock and metal. But this region was not always destined to be a debris field. Evidence suggests that in the early days of the solar system, a planet tried to form here, a fifth rocky world in our solar family. But it never stood a chance. Jupiter's immense gravity acted as a cosmic disruptor, its relentless pull stirring up the ancient building blocks of planets, the planetesimals, with such force that they could never coalesce. They were instead sent crashing into one another, shattering into the countless fragments we see today. The asteroid belt is, therefore, a planetary ghost, the remnant of a world that was gravitationally bullied out of existence by its giant neighbor. Journeying farther from the sun, we leave this powerful king behind and approach the second largest planet, the undisputed jewel of the solar system, Saturn. While it is a gas giant of impressive size, nearly as large as Jupiter, Saturn's identity is defined by its breathtaking and extensive ring system. These are not solid structures, but a vast, shimmering disk composed of countless individual particles of water ice and a smaller amount of rocky material, ranging in size from tiny dust grains to objects as large as mountains. The rings are incredibly wide, stretching out for 282,000 kilometers, or about 175,000 miles, from the planet's cloud tops. Yet they are astonishingly thin, with an average thickness of only about 10 meters, or roughly 30 feet. This incredible disparity in scale makes them one of the most delicate and beautiful structures in the cosmos. Saturn is not just a planet with rings. It is a miniature solar system in its own right, orbited by a large and diverse family of moons. As of our current count, we know of 82 moons in orbit around Saturn, a retinue of worlds that includes icy giants, captured asteroids, and strange, cratered landscapes. This complex system of rings and moons makes Saturn a place of endless scientific fascination, a celestial court surrounding a majestic, golden-hued monarch. But this monarch holds a surprising secret. Despite its colossal size, Saturn is the least dense planet in the solar system. It is composed primarily of the two lightest elements in the universe, hydrogen and helium. Its average density is actually less than that of water. This leads to a famous and rather delightful thought experiment. If you could find a cosmic bathtub large enough to hold it, Saturn would float. This single fact beautifully illustrates the alien nature of the gas giants, worlds whose very substance is fundamentally different from our solid, rocky home. Our voyage now takes us into the deeper, colder twilight of the outer solar system, to a world that remained unknown to the ancients. Here, we find Uranus, a planet whose quiet, pale blue face conceals a truly bizarre and violent history. Its most striking feature is its orientation. While other planets spin like tops as they orbit the sun, Uranus is the only one that rotates on its side. It is tilted at an extreme angle of 98 degrees, meaning its axis of rotation is almost parallel to its orbital plane. It effectively rolls along its orbital path, a celestial oddity that defies all planetary norms. The most likely explanation for this extreme tilt is a cataclysmic collision with an Earth-sized protoplanet billions of years ago. A cosmic blow that knocked the young world onto its side, where it has remained ever since. The planet's serene, featureless appearance is due to its atmosphere. The pale blue-green, or cyan, color is not from water, but from the presence of methane gas in its upper layers. This gas is very good at absorbing red and orange light from the sun, while reflecting the blue and green wavelengths back into space, giving Uranus its distinctive tranquil hue. This placid color, however, belies a world of extreme seasonal change. Because of its great distance from the sun, a single year on Uranus, one complete orbit, takes a staggering 84 Earth years to complete. When you combine this incredibly long year with the planet's extreme sideways tilt, you get the most bizarre seasons in the solar system. For a period of more than 20 years at a time, one of the planet's poles is pointed directly at the sun, experiencing 2 decades of continuous daylight and summer heat. At the same time, the opposite pole is plunged into an equally long winter of perpetual darkness and cold. As the planet continues its slow journey around the sun, these conditions gradually reverse, leading to seasons of a length and extremity that are truly beyond any human experience. Continuing our journey to the solar system's outer edges, we arrive at the last of the gas giants, a world of deep, mesmerizing blue, Neptune. Here, in the profound cold and darkness so far from the sun, we find a planet of chilling extremes. Neptune holds the title of the coldest planet in the solar system, a frigid world where the average temperature at its cloud tops plummets to a staggering minus 214 degrees Celsius, or a brutal minus 353 degrees Fahrenheit. This is a cold so intense that gases we think of as permanent, like nitrogen, freeze into solid ice. The planet radiates more heat from its interior than it receives from the distant sun, a sign of a still warm core that drives its surprisingly dynamic and violent atmosphere. And it is this atmosphere that holds another of Neptune's records. Despite the incredible cold and the faint solar energy, Neptune is home to the fastest and most powerful winds in the entire solar system. These are not mere gales. They are supersonic jet streams, vast rivers of frozen methane and other gases that scream around the planet at speeds reaching an astonishing 2,400 kilometers per hour, or nearly 1,600 miles per hour. This is faster than the speed of sound on Earth, and far more powerful than any hurricane ever recorded on our world. These ferocious winds whip up massive, dark storms in the planet's atmosphere, the most famous of which was the Great Dark Spot, a storm system similar in nature to Jupiter's Great Red Spot, but far more transient. This is a world where the weather is not just extreme. It is defined by a relentless, supersonic fury. The passage of time on Neptune is as grand and slow as its winds are fast. A single year on this distant world, the time it takes to complete one full orbit around the Sun, is equivalent to 164.8 Earth years. Since its official discovery in the mid-19th century, Neptune has only completed one full orbit of the Sun. For a human lifetime, a year on Neptune would be an eternity, a slow, majestic crawl through the dim twilight of the outer solar system. As we've journeyed through this planetary family, we've encountered not just the planets themselves, but their many companions. Moons are not a rarity in our solar system. They are a common feature of our cosmic neighborhood. In total, scientists have discovered and cataloged over 200 moons orbiting the planets, a diverse collection of worlds that range from captured asteroids to bodies larger than planets. Each one is a unique destination, with its own geology, history, and secrets. The king of all these moons is Ganymede, a satellite of Jupiter that holds the title of the largest moon in the solar system. It is a world of such impressive scale that it is actually larger than the planet Mercury. If it were orbiting the Sun on its own, it would undoubtedly be classified as a planet. Ganymede is a complex world of ice and rock, with a grooved, fractured surface that hints at a geologically active past. Incredibly, it is also the only moon known to generate its own magnetic field, a feature that suggests a liquid iron core, much like Earth's. This celestial giant is a world in its own right, a planet-sized moon locked in orbit around an even larger parent. Not to be outdone, Saturn boasts the second largest moon in the solar system, a world named Titan. Titan is unique for a different reason. It is the only moon with a thick, substantial atmosphere, one that is even denser than Earth's. This hazy, orange atmosphere is composed mostly of nitrogen, with a significant amount of methane and other hydrocarbons. Beneath this thick veil of clouds lies a landscape that is shockingly Earth-like, but with a profoundly alien chemistry. It has rivers, lakes, and even seas, but these are not filled with water. On Titan, where the surface temperature is a frigid minus 179 degrees Celsius, or minus 290 degrees Fahrenheit, liquid methane and ethane play the role of water, carving channels and pooling in vast, dark basins. It is a world of methane rain and hydrocarbon sand dunes, a cold, dark mirror of our own planet's hydrology. While the outer solar system is home to these giants, the inner planets also have their own companions, albeit on a much smaller scale. Mars is orbited by two tiny moons, Phobos and Deimos, and of these, Deimos is the smallest known moon in the entire solar system. It is a lumpy, potato-shaped rock, only about 12 kilometers, or 7.5 miles, in diameter. It is so small that if you were standing on the surface of Mars, it would appear not as a disk, but as a bright star in the night sky. Both of Mars's moons are thought to be captured asteroids, wanderers from the nearby asteroid belt that strayed too close and were ensnared by the red planet's gravity. Beyond the realm of the 8 major planets, our understanding of the solar system has expanded to include a new class of celestial bodies. The International Astronomical Union, the official body responsible for naming and classifying celestial objects, now recognizes 5 dwarf planets. These are worlds that are large enough to have been rounded by their own gravity, but have not cleared their orbital neighborhood of other debris. The current members of this exclusive club are Ceres, Pluto, Haumea, Makemake, and Eris. Each is a unique and distant world, a resident of the solar system's remote and icy frontiers. The most famous of these, of course, is Pluto. For over 70 years, it held the status of the 9th planet, a small, icy world at the edge of the known solar system. But in 2006, the International Astronomical Union made the controversial decision to reclassify it as a dwarf planet. This demotion was based on the new, more stringent definition of a planet, which required a celestial body to have gravitationally dominated its own orbit. Pluto, which shares its orbital space with many other objects in the Kuiper belt, did not meet this new criterion. The decision sparked a fierce debate among scientists and the public, a conversation that highlighted our ever-evolving understanding of the cosmos. Despite its change in status, Pluto remains a fascinating and complex world. Far from being a simple ball of ice and rock, it is a dynamic place with a surprisingly varied and active geology. The New Horizons spacecraft, which flew by Pluto in 2015, revealed a stunning landscape of towering mountains made of water ice, vast plains of frozen nitrogen, and a thin, hazy atmosphere. It is a world that has challenged all our expectations, proving that even the smallest, most distant members of our solar family can hold incredible surprises. Pluto is also the center of its own miniature system, with 5 known moons in orbit around it. The largest of these is Charon, a moon so large in comparison to Pluto that the two are often considered a binary system. Charon is more than half the diameter of Pluto, and the two are tidally locked, meaning they always show the same face to each other as they orbit a common center of gravity that lies in the space between them. The other 4 moons, Styx, Nix, Kerberos, and Hydra, are much smaller, irregularly shaped bodies that orbit this central, binary pair in a complex and chaotic dance. This intricate system is a testament to the dynamic and often violent history of the outer solar system. The discovery of moons is not limited to planets and dwarf planets. Even the smaller inhabitants of our solar system can have companions of their own. For a long time, asteroids were thought to be solitary objects, lonely wanderers tumbling through the void. But in 1993, this perception was shattered. The Galileo spacecraft, on its way to study Jupiter, made a close flyby of a main belt asteroid named Ida. The images it sent back to Earth contained a stunning surprise: a tiny moon, just over 1.5 kilometers, or about 1 mile, in diameter, orbiting the larger asteroid. This little moon was named Dactyl, and its discovery was a landmark moment in planetary science. It proved for the first time that asteroids, these relatively small, rocky bodies, could have their own satellites. Since then, we have discovered hundreds of asteroids with moons, some of which are binary systems where two objects of similar size orbit each other, while others are larger bodies with one or more smaller companions. These systems provide invaluable information about the mass and density of asteroids, helping us to understand their composition and origins. Dactyl and its parent, Ida, are residents of the main asteroid belt, a vast, donut-shaped region of space located between the orbits of Mars and Jupiter. This is not the tightly packed, chaotic debris field often depicted in science fiction. While it contains millions of rocky objects, the space between them is immense. If you were to fly a spacecraft through the heart of the belt, the chances of accidentally colliding with an asteroid would be infinitesimally small. The objects within this belt range in size from tiny pebbles to colossal bodies, hundreds of kilometers across. It is a cosmic junkyard, filled with the leftover building materials from the formation of the solar system, the raw ingredients of a planet that never was. Venturing even further out, beyond the orbit of Neptune, we enter another, even larger and more mysterious realm: the Kuiper Belt. This is a frigid, dark expanse, a second, much larger asteroid belt composed not of rock, but of countless icy bodies. These are the frozen relics from the dawn of the solar system, primordial objects known as Kuiper Belt objects, or KBOs. This region is home to many of the dwarf planets, including Pluto, Haumea, and Makemake. The Kuiper Belt is a place of profound cold and darkness, a vast, icy frontier that we are only just beginning to explore. It is believed to be the source of most of the short-period comets we see, those icy visitors that complete an orbit of the Sun in less than 200 years. But even this immense belt is not the final frontier of our solar system. Surrounding everything, like a vast, spherical shell, is the theoretical Oort cloud. This is a truly colossal structure, a sphere of icy objects thought to extend from just beyond the Kuiper Belt out to a distance of perhaps 100,000 times the distance from the Earth to the Sun, which is over 1.5 light years away. It is so far out that its outer edge is nearly a quarter of the way to the nearest star. This cloud is a cosmic deep freeze, a repository of trillions of comets held in a loose gravitational embrace by our distant sun. These are the long-period comets, those that take thousands or even millions of years to complete a single orbit. The Oort cloud has never been directly observed. Its existence is inferred from the orbits of these comets. Occasionally, a passing star or a galactic tide will give one of these icy bodies a gravitational nudge, sending it on a long, slow journey towards the inner solar system, where it may blaze across our skies as a spectacular comet. It is a humbling thought that all the comets we have ever witnessed, these celestial messengers from the dawn of time, originate from within our own solar system. Whether they are launched from the icy depths of the Oort cloud or kicked out of the Kuiper belt, they are our neighbors, ancient members of our cosmic family. One of the most famous of these celestial visitors is Halley's Comet. It is a short-period comet returning to the inner solar system on a predictable schedule. Its journey around the Sun takes approximately 76 years, a time span that is close enough to a human lifetime to make it a recurring and deeply personal celestial event. It has been observed and recorded by astronomers around the world for at least 2,000 years, a constant and reliable presence in our historical skies. Its regular appearances have allowed us to study comets in detail, to understand their composition and behavior as they are warmed by the sun. Another well-known visitor is Comet Hale-Bopp, which graced our skies in the late 1990s. This was a long-period comet, a true giant from the Oort cloud, with an orbital period of about 2,533 years. Its visit was a once-in-a-millennium event, a spectacular display that was visible to the naked eye for a record-breaking 18 months. Its immense size and activity made it one of the brightest comets of the 20th century, a brilliant reminder of the vast, frozen reservoir of worlds that lies at the farthest reaches of the Sun's domain. Our solar system, with its planets, belts, and clouds, is not an island universe. It is a small part of a much grander structure, a vast, swirling city of stars known as the Milky Way galaxy. Our Sun is just one of hundreds of billions of stars in this galaxy, a fairly average, middle-aged star located in one of its spiral arms, about 2/3 of the way out from the galactic center. When you look up at the night sky and see the faint, glowing band of the Milky Way, you are looking into the dense, star-filled plain of our own galaxy. And within this single galaxy, our solar system is likely not unique. Based on recent discoveries of exoplanets, planets orbiting other stars, scientists now estimate that there could be as many as 100 billion solar systems in the Milky Way alone. The number is almost beyond comprehension, suggesting a universe teeming with worlds, a cosmos where planets are more the rule than the exception. Even with this staggering number of potential neighbors, the distances between stars are almost unimaginably vast. The nearest star system to our own is Proxima Centauri, a small, dim, red dwarf star that is part of the Alpha Centauri triple star system. It is located 4.24 light-years away. A light-year is the distance light travels in a year, which is about 9.5 trillion kilometers, or nearly 6 trillion miles. This means that the light we see from our closest stellar neighbor has been traveling through space for over 4 years to reach us. A journey across an ocean of emptiness that separates these islands of starlight. Despite these colossal interstellar distances, some members of our celestial family are close enough to feel like personal companions in our night sky. The planet Venus, named for the Roman goddess of love and beauty, certainly lives up to its namesake's reputation for capturing attention. Due to its thick, highly reflective cloud layer and its relative proximity to Earth, Venus is the brightest planet in our sky and the second brightest natural object after the Moon. It is so brilliant that it can sometimes be seen from Earth with the naked eye even during the day. A tiny, sharp pinprick of light against the blue canvas of our atmosphere, provided you know exactly where to look. More commonly, it appears as a dazzling beacon in the twilight hours, earning it the dual titles of the morning star and the evening star. It is not a star, of course, but a world, a neighbor whose reflected sunlight has guided travelers and inspired poets for millennia. Venus is one of a select group of planets that are easily visible without the aid of a telescope. This exclusive celestial club, known as the Naked Eye planets, consists of 5 members: Mercury, Venus, Mars, Jupiter, and Saturn. These were the only planets known to ancient astronomers, the celestial wanderers whose stately procession against the backdrop of fixed stars formed the basis of early astronomy and mythology. Observing their movements, their predictable yet complex dance, was a foundational human experience, a way of connecting with the grand, clockwork machinery of the cosmos. For most of human history, these 5 planets, along with our Sun and Moon, constituted the entirety of the known solar system. While we have spent centuries looking up at these worlds, the last century has seen a dramatic shift in our perspective. We have begun to leave our own world behind, to venture into the space between the planets. This journey into the void has revealed some of the profound and often surprising ways that the human body reacts to a weightless environment. One of the most striking changes is an increase in height. Without the constant downward pull of Earth's gravity compressing their spines, astronauts can grow up to 5 centimeters, or about 2 inches, taller while in space. The vertebrae are free to separate slightly, leading to a temporary and quite literal growth spurt. This effect is not permanent. Upon returning to Earth's gravity, they gradually shrink back to their original height, but it is a dramatic illustration of how deeply our bodies are adapted to the conditions of our home planet. Another peculiar and less glamorous side effect of life in microgravity involves the feet. On Earth, the soles of our feet are constantly in use, bearing our weight, toughening our skin, and connecting us to the ground. In space, astronauts float from place to place, and their feet are rarely used for walking. As a result, the thick, calloused skin on the soles of their feet begins to soften and peel off, much like the skin after a bad sunburn. This process is a strange and intimate reminder that even our own bodies can become alien to us when we leave our terrestrial cradle. Our presence in space, however, has not been without consequences. The regions of space immediately surrounding our planet are becoming increasingly cluttered. For more than 60 years, we have been launching satellites, rockets, and probes. And not all of this hardware has returned to Earth or been safely deorbited. The result is a growing cloud of space junk, a collection of over 500,000 pieces of debris that are currently being tracked in orbit. This includes everything from defunct satellites and spent rocket stages to tiny fragments of metal and paint flecks. While they may be small, these objects are traveling at incredible speeds, thousands of kilometers per hour. And even a tiny piece of debris can cause catastrophic damage to a functioning satellite or a crewed spacecraft. This orbital junkyard is a serious and growing problem, a form of environmental pollution on a cosmic scale that threatens our future access to space. Venturing into this environment requires an extraordinary level of protection. The space suit, or extravehicular mobility unit, as it is officially known, is not merely a piece of clothing. It is a personalized spacecraft. A full National Aeronautics and Space Administration, or NASA, spacesuit is a marvel of engineering, a multi-layered, self-contained environment that provides everything an astronaut needs to survive in the vacuum of space. It supplies oxygen, removes carbon dioxide, maintains a stable pressure and temperature, and protects against radiation and micrometeoroid impacts. This complexity comes at a steep price. The cost of a single, complete NASA spacesuit is estimated to be approximately 12 million United States dollars. It is one of the most expensive and sophisticated pieces of equipment ever created, a testament to the incredible challenges of keeping a human being alive in the most hostile environment imaginable. Our ventures into space have so far been limited to our immediate cosmic neighborhood, with human footsteps gracing only one other celestial body, our moon. The Apollo missions of the mid-20th century left an indelible mark on lunar history, both figuratively and literally. On the airless, weatherless surface of the moon, there is no wind to blow away the dust, and no water to wash away impressions. The footprints left behind by the Apollo astronauts in the fine lunar soil, the regolith, are preserved in a near-perfect state. Barring a direct micrometeorite strike, these imprints of human presence will likely remain undisturbed for an astonishing 100 million years, a silent, enduring monument to our first tentative steps into a larger world. At the heart of this world, and indeed our entire solar system, is the star that makes it all possible. Our sun is a star of a specific type, classified by astronomers as a yellow dwarf. This is a somewhat misleading name, as the sun is far from small in human terms. It is a stable, main sun sequence star, currently in the prime of its life, fusing hydrogen into helium in its core at a prodigious rate. It is this process of nuclear fusion that generates the immense energy that warms our planet and powers life on Earth. The journey of this energy from the sun's core to its surface is an epic saga in itself. A photon of light, a single particle of energy, is not created at the surface. It is born in the incredible heat and pressure of the solar core. From there, it begins a long and tortuous journey outwards. It does not travel in a straight line. Instead, it is absorbed and re-emitted countless times by the dense plasma of the sun's interior, zigzagging its way on a random walk that can take an astonishing 100,000 years to complete. The sunlight that warms your face today began its journey from the center of the sun before modern humans had even begun to build cities. Once it finally reaches the surface, it is free to travel outwards into space. But its initial journey is a powerful reminder of the sheer density and scale of our star. Ultimately, it is the sun's immense gravitational pull that orchestrates the entire cosmic ballet of the solar system. This is the fundamental force that keeps every planet, from Mercury to Neptune, locked in its stable, predictable orbit. The planets are in a constant state of falling towards the sun, but their immense sideways motion, their orbital velocity, means they continually miss it, resulting in the graceful, elliptical paths they trace through space. This perfect balance between gravity and momentum is the invisible architecture of our solar system, the force that brings order to the celestial chaos and makes our cosmic home a stable and predictable place. For millennia, our understanding of planets was confined to the celestial bodies within our own solar family. The idea of worlds orbiting other stars was a staple of philosophical speculation and science fiction. But there was no concrete proof. This changed dramatically in the late 20th century. In 1992, a discovery was made that would forever alter our perception of the cosmos. Astronomers Alexander Wolszczan and Dale Frail, studying a distant, spinning stellar corpse known as a pulsar, noticed irregularities in the timing of its radio pulses. These variations could only be explained by the gravitational tug of planets in orbit around it. This was the first definitive detection of an exoplanet, a planet outside our solar system. It was a watershed moment, the beginning of a new era in astronomy that transformed exoplanets from theoretical possibilities into observable realities. Since that groundbreaking discovery, our catalog of known exoplanets has grown exponentially, with thousands of worlds now confirmed. For most of this time, our methods of detection were indirect, relying on observing the subtle effects a planet has on its parent star, such as the slight dimming of starlight as a planet passes in front of it, a method known as transit photometry, or the gravitational wobble it induces, known as the radial velocity method. Seeing an exoplanet directly is an immense technical challenge, as the faint light of a planet is easily lost in the overwhelming glare of its host star. But in 2022, we crossed another major threshold. The James Webb Space Telescope, the most powerful and sophisticated observatory ever launched, used its advanced optics and infrared sensitivity to capture the first ever direct image of a planet outside our solar system. The target was a gas giant several times more massive than Jupiter, orbiting a star nearly 400 light-years away. For the first time, we could see an exoplanet as a distinct point of light, a tangible world separate from its star. This achievement opens up exciting new possibilities for studying the atmospheres of these distant worlds, searching for the chemical fingerprints of life. While these recent discoveries are pushing the boundaries of our knowledge, our map of our own solar system is also a relatively modern creation, pieced together over centuries of patient observation and occasional serendipity. For most of human history, the known planets ended at Saturn. The vast, dark regions beyond were a complete mystery. This changed in the late 18th century, thanks to the meticulous work of the astronomer William Herschel. In 1781, while systematically surveying the night sky with his powerful, custom-built telescope, Herschel noticed an object that was not a star. It appeared as a small, fuzzy disk, and over several nights, he observed that it moved relative to the background stars. He initially thought he had discovered a new comet, but further calculations of its orbit revealed that it was a planet, a new major world orbiting the Sun far beyond Saturn. This was the planet Uranus, the first to be discovered in modern times, a discovery that instantly and dramatically doubled the known size of the solar system. The discovery of Uranus was a triumph of observational astronomy. But the story of the next planet is one of mathematics and the power of theoretical prediction. In the decades following Uranus's discovery, astronomers noticed that its orbit was not quite what it should be. It deviated slightly from the path predicted by Newton's laws of gravity. Some astronomers hypothesized that there must be another, even more distant planet whose gravitational pull was gently tugging on Uranus, causing these orbital anomalies. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently set out to solve this celestial mystery. Using only the data from Uranus's perturbed orbit and the principles of gravitational theory, they both calculated the predicted position of this unseen world. In 1846, German astronomer Johann Galle, using Leverrier's calculations, pointed his telescope to the predicted location and, within a single night of searching, found the new planet. It was Neptune, a world discovered not by chance, but by the sheer intellectual force of mathematical prediction. It was a stunning confirmation of gravitational theory and a testament to the power of the human mind to map the unseen cosmos. The final chapter in the initial exploration of our solar system's planetary census came in the early 20th century. Following the discovery of Neptune, astronomers still noted some minor discrepancies in the orbits of the outer planets, leading them to suspect the existence of a Planet X lurking in the darkness. Percival Lowell, a wealthy and enthusiastic astronomer, founded an observatory in Arizona and began a systematic photographic search for this elusive world. The search continued for years, even after Lowell's death. In 1930, a young, self-taught astronomer named Clyde Tombaugh, working at the Lowell Observatory, was painstakingly comparing photographic plates of the night sky taken several days apart. He was looking for any tiny point of light that had moved against the background of fixed stars. After months of tedious work, he found one. It was a faint, slow-moving object in the constellation Gemini, far beyond the orbit of Neptune. This was Pluto, the long sought-after ninth planet. For decades, it held its place as the final icy outpost of our solar system, a small, mysterious world whose discovery was a story of persistence and meticulous observation. The vastness of space, even within our own solar system, presents a profound challenge to travel. To illustrate this, consider the journey of the Voyager 1 spacecraft. Launched in the 1970s, it is one of the fastest objects ever built by humanity, currently traveling at a blistering speed of over 60,000 kilometers per hour, or about 35,000 miles per hour. Even at this incredible velocity, if Voyager 1 were pointed in the direction of our nearest stellar neighbor, Proxima Centauri, it would take about 70,000 years to complete the journey. This calculation lays bare the immense, almost incomprehensible scale of interstellar distances and the formidable challenge of one day reaching the stars. While Saturn is famous for its magnificent and highly visible rings, it is not the only giant in our solar system to possess them. Jupiter, the king of the planets, also has a faint ring system of its own, discovered by the Voyager. One spacecraft during its flyby, Jupiter's rings are composed of dark dust particles kicked up from its inner moons by micrometeoroid impacts. They are much darker and less substantial than Saturn's icy rings, making them impossible to see from Earth with all but the largest telescopes. They are a subtle and ghostly feature, a delicate halo around a colossal world. Returning to the inner solar system, we find a world where the conditions are the antithesis of the cold, dark void. The atmospheric pressure on the surface of Venus is a crushing force, over 90 times greater than the sea level pressure on Earth. This is an environment of extremes, where the weight of the air itself is a significant geological force. This immense pressure is a direct result of its thick, dense atmosphere, which is composed almost entirely of carbon dioxide. Standing on the surface of Venus would be equivalent to being nearly a kilometer, or over half a mile, deep in one of Earth's oceans. A pressure that would instantly crush most terrestrial structures. Our neighbor Mars, in contrast, presents a much gentler, though still alien, environment. It is accompanied on its journey around the Sun by two small, irregularly shaped moons, Phobos and Deimos. These are not the grand, spherical worlds we see orbiting the gas giants. They are small, cratered bodies, likely captured asteroids, that circle the red planet in close, fast orbits. Phobos, the larger of the two, is so close that it orbits Mars 3 times in a single Martian day. The final fact in this segment of our journey brings us back to the jewel of the solar system. The magnificent rings of Saturn, that shimmering, ethereal structure, are made almost entirely of particles of water, ice, and rock. This was one of the key discoveries made by the Cassini spacecraft during its long and detailed study of the Saturnian system. The brightness and purity of the rings are a direct result of their icy composition. They are not a solid, continuous structure, but a vast, orbiting river of countless individual pieces, a celestial spectacle of unparalleled beauty, all crafted from the simplest of frozen molecules. As we venture back to the strange, sideways world of Uranus, we find that it too possesses a retinue of moons, each with its own unique character. The planet is orbited by 27 known satellites, all named not for figures from Roman or Greek mythology, but for characters from the works of William Shakespeare and Alexander Pope. Among this literary cast of celestial bodies, the largest and perhaps most enigmatic is Miranda. Discovered in the mid-20th century by Gerard Kuiper, Miranda is a world of breathtaking geological chaos. When the Voyager, 2 spacecraft, flew past in 1986, it sent back images of a surface that looked like a bizarre, cosmic jigsaw puzzle. It is covered in a jumble of vastly different terrains, with old, heavily cratered regions abutting younger, dramatically grooved areas, and enormous canyons that slice through the landscape. One of these canyons, Verona Rupes, is a colossal cliff that is estimated to be at least 5 kilometers, or about 3 miles, deep. Due to Miranda's low gravity, a rock dropped from the top of this cliff would take a full 12 minutes to reach the bottom. The moon's fractured appearance suggests a violent past, a history where it may have been shattered into pieces by a massive impact and then haphazardly reassembled by gravity, creating the strange and patchwork world we see today. Continuing our outward journey to the deep blue realm of Neptune, we encounter its largest moon, Triton. This is a world of profound, cold, and fascinating contradictions. Triton is unique among the large moons of the solar system because it orbits Neptune in the opposite direction of the planet's rotation, a retrograde orbit. This is a strong indication that Triton was not formed in orbit around Neptune, but is instead a captured object, likely a dwarf planet from the Kuiper belt that strayed too close and was ensnared by Neptune's powerful gravity. This violent capture would have had catastrophic effects on Neptune's original moon system and would have also heated Triton, leading to a period of geological activity. Today, Triton is one of the coldest objects in the solar system, with a surface temperature of minus 235 degrees Celsius, or minus 391 degrees Fahrenheit. Yet, despite this deep freeze, its surface is remarkably young and active, featuring vast plains of frozen nitrogen, a cantaloupe-like terrain of icy dimples, and active cryovolcanoes, or ice volcanoes, that spew plumes of nitrogen frost and dark organic compounds high into its thin atmosphere. Triton is a captured wanderer, a frozen, active world that tells a story of a dynamic and often violent outer solar system. Our journey now takes us to the most famous resident of that distant region, the dwarf planet Pluto. Here, at the edge of the classical solar system, the temperatures are almost unimaginably cold. On Pluto's surface, the temperature can plummet to as low as minus 225 degrees Celsius, which is a staggering minus 375 degrees Fahrenheit. This is so cold that common gases like nitrogen, methane, and carbon monoxide, which make up most of Pluto's thin atmosphere, exist as solid ices on the surface, forming vast glaciers and towering mountains of frozen material. This is a world sculpted by a cold that is almost absolute, a place where water ice is as hard as rock and nitrogen ice flows like glaciers on Earth. Despite its small size, the central star of our solar system, the Sun, is an object of truly monumental proportions. It is so large that its volume is great enough to contain approximately 1 million planets the size of Earth. If you could imagine the Sun as a hollow ball, you could pack it to the brim with 1 million Earths and still have room to spare. This single comparison beautifully illustrates the sheer scale of our star and its overwhelming dominance in the solar system. It is the gravitational anchor and the energy source for every world in its domain, a celestial furnace of almost incomprehensible size. Like all celestial bodies, the Sun is not static. It rotates on its axis. However, because it is a ball of plasma and not a solid body, it experiences differential rotation. This means that it rotates at different speeds, at different latitudes. The Sun's equator completes a rotation in about 25 Earth days, while its poles take longer, around 35 days. On average, we can say that the sun rotates on its axis about once every 27 days. This rotation is a fundamental aspect of its behavior, as it helps to drive the sun's powerful magnetic field, which in turn is responsible for phenomena like sunspots, solar flares, and the solar wind. Our closest celestial companion, the moon, holds a special place in our history and our skies. It is Earth's only natural satellite, a constant and familiar presence that has governed our tides, inspired our myths, and served as our first stepping stone into the cosmos. It is a silent, airless world, a museum of cosmic history, its surface covered in the craters and scars of billions of years of impacts. The relationship between the Earth and the moon is an intimate one, a gravitational dance that has shaped both worlds. A fascinating consequence of this dance is that the same side of the moon always faces the Earth. This phenomenon is known as synchronous rotation, or tidal locking. Over billions of years, the Earth's gravitational pull on the moon has slowed its rotation to the point where its rotational period is exactly the same as its orbital period. It takes the moon about 27 days to rotate once on its axis, and it takes the same amount of time to complete one orbit of the Earth. The result is that we are always looking at the same hemisphere, the near side, while the far side remained a complete mystery until the dawn of the space age. This constant, familiar face of the moon is a direct result of the deep and ancient gravitational bond it shares with our planet. The gravitational pull of the moon is, of course, much weaker than our own. Because it is much smaller and less massive than the Earth, the moon's surface gravity is only about 1/6 of Earth's gravity. This means that a person who weighs 180 pounds on Earth would weigh only about 30 pounds on the moon. This low gravity is what allowed the Apollo astronauts to take their famous bounding leaps across the lunar surface, an experience of lightness and freedom that is impossible to replicate in our own high-gravity environment. Our journey through the solar system has now returned us to the realm of the smaller bodies, to the rocky and icy debris that populates the space between the planets. We now know that in the main asteroid belt, a graveyard of ancient comets exists. These are objects that were once active comets, spewing gas and dust as they were warmed by the sun, but have since exhausted all their volatile materials, leaving behind a dormant, rocky nucleus. They are now indistinguishable from normal asteroids. However, scientists believe that some of these cometary ghosts could still have ice buried deep within their interiors. If their orbit were to be slightly changed, perhaps by a gravitational nudge from Jupiter, bringing them closer to the sun, this buried ice could once again begin to vaporize, and these ancient comets could be reawakened, once again growing tails and blazing across the sky. This graveyard is a reminder of the cyclical and ever-changing nature of the solar system. Finally, not all asteroids are content to remain in the main belt. Some have orbits that bring them much closer to our own world. These are known as near-Earth asteroids, or NEAs. They are a diverse group of objects whose orbits cross or come close to Earth's orbit. These asteroids are of great scientific interest because they are relatively easy to visit with spacecraft, and they may one day be a source of valuable resources. However, they also represent a potential hazard. The impact of a large near-Earth asteroid could have catastrophic consequences for life on Earth. For this reason, astronomers around the world are engaged in a dedicated effort to find, track, and characterize these objects. A celestial neighborhood watch program designed to protect our planet from a potential cosmic collision. Comets, these celestial wanderers, are fundamentally different from the rocky asteroids we've been discussing. They are often described as dirty snowballs, a wonderfully evocative and largely accurate description. Their solid nucleus is composed of a mixture of water ice, frozen gases like carbon dioxide, methane, and ammonia, and a significant amount of dust and dark organic compounds. These organic molecules, carbon-based compounds that are the building blocks of life, are of immense interest to astrobiologists. It is thought that in the early days of the solar system, cometary impacts on a young Earth may have delivered a significant amount of both water and these essential organic materials, potentially seeding our world with the raw ingredients necessary for life to emerge. These cosmic snowballs are time capsules, preserving the pristine, primordial material from the outer nebula where the planets first formed 4.5 billion years ago. As a comet on its long, elliptical orbit approaches the inner solar system, it begins to warm up under the intensifying glare of the sun. This warmth causes the ices on its surface to sublimate, to turn directly from a solid into a gas. This process releases a vast cloud of gas and dust that envelops the nucleus, a glowing, hazy atmosphere known as the coma, which can grow to be hundreds of thousands of kilometers in diameter, larger than many planets. It is this coma that gives a comet its fuzzy, ethereal appearance. But the most spectacular feature of a comet, its defining characteristic, is its magnificent tail. The tail is not something that trails behind the comet like smoke from a chimney. It is an appendage that is actively pushed away from the comet by the power of the sun. In fact, a comet typically has two distinct tails. The first, the dust tail, is composed of the fine dust particles that are released along with the gas. These particles are pushed away by the pressure of sunlight itself, a gentle but relentless force. Because the dust particles are relatively heavy, they tend to follow the comet's orbital path, creating a broad, curved, and often yellowish tail. The second tail, the ion tail, or gas tail, is composed of the gases that have been ionized by the sun's powerful ultraviolet radiation. These charged particles are then caught up and pushed directly away from the sun by the solar wind, the constant stream of charged particles flowing from the sun's corona. This means the ion tail always points directly away from the sun, regardless of the comet's direction of travel. It is often a faint, straight, and bluish streamer, a celestial windsock showing the direction of the solar wind. While comets are visitors from the frozen depths of the outer solar system, our night sky is also filled with a much more frequent and fleeting phenomenon: meteors. These are the brilliant streaks of light we often call shooting stars. They are not stars at all, of course. A meteor is the visible path of a small piece of cosmic debris, a meteoroid, as it enters Earth's atmosphere at incredibly high speed. The intense friction with the air heats the meteoroid and the surrounding air to incandescence, creating the fiery streak we see. Most meteoroids are no bigger than a grain of sand, and they burn up completely at high altitudes, never reaching the ground. On any given night, you can see a few of these sporadic meteors, but on certain nights of the year, the heavens put on a spectacular show. Most of these tiny particles do survive their fiery descent, however. Occasionally, a larger meteoroid, a piece of an asteroid, or perhaps even a piece of another planet, is tough enough to withstand the incredible heat and pressure of its journey through our atmosphere. If it survives and lands on the Earth's surface, it is then called a meteorite. These are our tangible connection to the cosmos, rocks from space that we can hold in our hands. They come in various types, from stony meteorites that resemble terrestrial rocks to iron meteorites that are composed of a dense nickel-iron alloy. By studying their composition and structure, scientists can learn a great deal about the conditions in the early solar system, the makeup of asteroids, and the geological history of other worlds. They are scientific treasures, cosmic messengers that have completed an incredible journey to land at our feet. The phenomenon of a meteor shower occurs when the Earth, in its orbit around the Sun, passes through a particularly dense trail of debris left behind by a comet, or, in some cases, an asteroid. As a comet orbits the Sun, it is constantly shedding dust and small particles, leaving a stream of this material along its orbital path. When the Earth intersects this stream, we experience a meteor shower, as thousands of these tiny particles burn up in our atmosphere. Because all the debris is traveling in the same direction, the meteors in a shower appear to radiate from a single point in the sky, known as the radiant. Meteor showers are named after the constellation where their radiant appears to be located, giving us familiar showers like the Perseids in August and the Geminids in December. They are a beautiful and predictable celestial event, a direct and visible interaction between our planet and the ghostly trail of a passing comet. The question of where our atmosphere ends and space begins is not a simple one, as there is no sharp, defined boundary. The atmosphere simply gets thinner and thinner with increasing altitude. However, for the purposes of international law and aerospace records, an imaginary line has been established. This is the Kármán line, named after the physicist Theodor von Kármán, who first calculated it. It is located at an altitude of 100 kilometers, or about 62 miles, above sea level. This is the altitude at which the atmosphere becomes so thin that a conventional aircraft would have to travel faster than orbital velocity to generate enough aerodynamic lift to stay aloft. It is the internationally accepted, if arbitrary, starting point of space, the line that separates aeronautics from astronautics. While our solar system is filled with a wondrous variety of worlds, the universe may hold planets of an even more exotic and valuable nature. Astronomers have discovered an exoplanet named 55 Cancri E, which is located about 40 light-years away and is twice the size of Earth. Based on studies of its mass and radius, scientists have hypothesized that this super-Earth may have a composition that is rich in carbon. Under the immense pressure and temperature of its interior, this carbon could be compressed into its crystalline form, diamond. It is therefore possible that there exists a planet made substantially of diamond, a world of almost unimaginable wealth and beauty. This is still a matter of scientific debate, but it highlights the incredible diversity of worlds that may exist throughout the cosmos. Our own cosmic home, the Milky Way galaxy, is just one of countless such structures in the observable universe. It is a vast and beautiful spiral galaxy, but it is by no means unique. With powerful telescopes like the Hubble Space Telescope, we have been able to look deep into the universe and see that it is filled with galaxies of all shapes and sizes, stretching out in every direction as far as we can see. Current estimates suggest that there are at least 2 trillion galaxies in the observable universe. Our Milky Way is just one island of stars in a cosmic ocean of literally trillions of others, a fact that speaks to the almost infinite scale and richness of the cosmos. Within our own solar system, the planets can be neatly divided into 2 distinct groups, reflecting their different origins and compositions. The inner planets, Mercury, Venus, Earth, and Mars, are the terrestrial planets. They are relatively small, dense worlds, composed primarily of rock and metal, with solid surfaces and thin atmospheres. They formed in the hotter, inner region of the primordial solar nebula, where only materials with high melting points could condense into solid particles. The outer planets, Jupiter, Saturn, Uranus, and Neptune, are the gas giants, also known as the Jovian planets. They are colossal worlds with no solid surfaces, composed primarily of the light elements, hydrogen and helium, along with smaller amounts of ices like water, ammonia, and methane. They formed in the colder outer regions of the nebula, beyond the so-called frost line, where it was cold enough for these volatile ices to condense, allowing them to grow much larger and gravitationally capture the abundant hydrogen and helium gas that made up most of the nebula. This fundamental division is the primary architectural feature of our solar system. The immense energy that powers our entire solar system and makes life on Earth possible originates from the very heart of our star. Deep within the Sun's core, the conditions are almost beyond comprehension. The temperature is a staggering 15 million degrees Celsius, or about 27 million degrees Fahrenheit, and the pressure is over 200 billion times that of Earth's atmosphere at sea level. In this extreme environment, a process known as nuclear fusion takes place. The Sun's core is a natural fusion reactor, where hydrogen atoms, the most abundant element in the universe, are crushed together with such force that they overcome their natural electrical repulsion and fuse to form helium atoms. This process is not perfectly efficient. A tiny fraction of the mass of the hydrogen atoms is converted directly into a tremendous amount of energy, as described by Albert Einstein's famous equation, E equals mc squared. Every second, the Sun converts about 4 million tons of matter into pure energy, a torrent of light and heat that radiates outwards, eventually bathing the entire solar system. This process has been ongoing for billions of years and will continue for billions more, a stable and reliable source of power for all the worlds in its domain. The Sun's structure is layered like an onion, with the energy produced in the core making its way outwards through different zones. But the part of the Sun that is perhaps most mysterious and beautiful is its outermost atmospheric layer, a tenuous and incredibly hot region known as the corona. The corona is a wispy, ethereal halo of plasma that extends millions of kilometers or millions of miles into space. It is usually invisible to the naked eye, completely lost in the bright glare of the Sun's main surface, the photosphere. However, during a total solar eclipse, when the moon perfectly blocks the photosphere, the magnificent silvery white corona is revealed in all its glory. The most baffling thing about the corona is its temperature. While the surface of the Sun is a scorching 5,500 degrees Celsius, or about 10,000 degrees Fahrenheit, the corona is, inexplicably, much, much hotter, reaching temperatures of over 1 million degrees Celsius, or several million degrees Fahrenheit. How this outer layer is heated to such extreme temperatures, in defiance of the normal laws of thermodynamics, is one of the biggest unsolved mysteries in solar physics, a puzzle known as the coronal heating problem. Back in the realm of the planets, we find that Earth is not the only world to possess a powerful magnetic field. The giant planet Jupiter has a magnetosphere that is truly colossal, the largest and most powerful of any planet in the solar system. It is generated by the rapid rotation of a vast, deep layer of metallic hydrogen in its interior, a strange electrically conductive fluid that exists only under the immense pressures found inside a gas giant. Jupiter's magnetic field is nearly 20,000 times stronger than Earth's, and it creates a magnetosphere that is so enormous it would appear larger than the full moon in our night sky if it were visible to the naked eye. This magnetic bubble traps a torus of intense radiation, making the environment around Jupiter one of the most hazardous in the entire solar system. On the distant, deep blue world of Neptune, astronomers in the late 20th century observed a massive storm system that was strikingly similar to Jupiter's most famous feature. This storm, named the Great Dark Spot, was a colossal anticyclone, a high-pressure system about the size of the Earth, with ferocious winds raging around its edges. It was a dramatic and powerful feature, a dark, swirling vortex in the planet's azure cloud tops. However, when the Hubble Space Telescope turned its gaze towards Neptune, just a few years later, the Great Dark Spot had completely vanished. It was a surprising and stark reminder of how different the atmospheres of the gas giants are from our own. While Jupiter's Great Red Spot has persisted for centuries, Neptune's storms appear to be much more transient, forming and dissipating on a timescale of years or decades. The disappearance of the Great Dark Spot shows that even the most massive planetary features can be fleeting. Our modern exploration of the solar system has been carried out by a fleet of robotic emissaries, sophisticated spacecraft that have acted as our eyes and ears in the cosmos. One of the most celebrated of these modern explorers is NASA's New Horizons spacecraft. Launched in 2006, its primary mission was to conduct the first ever close-up study of the dwarf planet Pluto and its moons. After a journey of nearly a decade, spanning 5 billion kilometers, or 3 billion miles, New Horizons flew past Pluto in July of 2015, capturing stunning, high-resolution images and a wealth of scientific data. It revealed a world of unexpected geological complexity and beauty, transforming our view of Pluto from a distant, fuzzy point of light into a vibrant and active world. The New Horizons mission was a triumph of exploration, a testament to our ability to reach out and touch the most distant members of our solar family. Before New Horizons ventured to the icy fringes, another mission was busy rewriting the books on the middle part of our solar system. The Cassini spacecraft, a joint project of NASA and the European Space Agency, was a dedicated Saturn orbiter. It arrived at the ringed planet in 2004 and spent the next 13 years in orbit, conducting an incredibly detailed and comprehensive study of Saturn, its magnificent rings, and its fascinating family of moons. Cassini gave us breathtaking views of the rings, discovered new moons, and studied the strange, methane-rich world of Titan in unprecedented detail by deploying the Huygens probe to land on its surface. The mission ended in 2017 with a planned, dramatic plunge into Saturn's atmosphere, a final act designed to protect any potential life on Saturn's moons from earthly contamination. Cassini's legacy is a treasure trove of data that will keep scientists busy for decades to come. The interaction of a planet's magnetic field with the solar wind can create one of the most beautiful and awe-inspiring spectacles in nature, the aurora. On Earth, we know them as the aurora borealis, or northern lights, and the aurora australis, or southern lights. They are caused when charged particles from the sun, carried on the solar wind, are funneled by the Earth's magnetic field towards the poles. As these particles collide with atoms and molecules in our upper atmosphere, they excite them, causing them to glow in a shimmering, dancing curtain of green, red, purple, and blue light. This same phenomenon occurs on other planets with strong magnetic fields, like Jupiter and Saturn, creating auroras that are far larger and more powerful than our own. A beautiful and universal consequence of the constant interplay between a star and its planets. While our gaze is often turned towards the heavens, it is worth remembering the superlatives of our own world. The highest point on the surface of the Earth is the peak of Mount Everest in the Himalaya mountain range. Its summit stands at an elevation of 8,848 meters, or 29,032 feet, above sea level. It is a place of extreme cold and thin air, a formidable challenge that has drawn climbers and adventurers for over a century. It is the pinnacle of our planet's geology, the roof of our terrestrial world. Just as our planet has a highest point, it also has a deepest. The Mariana Trench, located in the western Pacific Ocean, is the deepest part of any of our planet's oceans. The deepest point within the trench, a small valley known as the Challenger Deep, reaches a depth of nearly 11,000 meters, or about 36,000 feet, below sea level. The pressure here is over 1,000 times that at the surface, and the darkness is absolute. It is a world of incredible extremes, more remote and less explored than the surface of the moon, a final, deep frontier on our own planet. Our entire story, this grand tour of planets, moons, and stars, all comes back to a single, humble origin. The solar system, in all its complexity and beauty, formed from a vast, rotating cloud of interstellar gas and dust known as the solar nebula. About 4.6 billion years ago, a nearby event, perhaps the shock wave from a supernova, caused this cloud to collapse under its own gravity. As it collapsed, it began to spin faster, flattening into a disk, much like a spinning ball of pizza dough. At the center of this disk, where the material was densest and hottest, a protostar ignited, which would eventually become our sun. In the cooler, outer parts of the disk, the remaining dust and gas began to clump together, forming the planets, moons, and all the other bodies that we see today. From this single, swirling cloud, our entire cosmic home was born. And so, our grand tour of this cosmic neighborhood draws to a close, bringing us back from the edge of interstellar space to this one singular world. From a swirling cloud of primordial gas and dust, a star was born, and in its gravitational embrace, a family of worlds coalesced. We have journeyed through this family, from the searing inferno of Venus to the silent, frozen plains of Pluto, from the ancient storms of Jupiter to the chaotic, fractured surface of Miranda. We have seen that our home is a place of both staggering scale and intricate detail, a system governed by ancient and unwavering physical laws. The story of the solar system is not a remote astronomical tale. It is our own origin story. The very elements that make up our world, our bodies, and our minds were forged in the hearts of stars long since dead and scattered across the nebula from which we were born. The iron in our blood, the calcium in our bones, all of it is a legacy of the cosmos. We are, in the most literal sense, a living, breathing part of this system, a way for the universe to look back upon and understand itself. And for all that we have learned, the story is far from over. The night sky, the same sky our distant ancestors looked upon with reverence and curiosity, remains a vast and profound mystery. Every new discovery, every image sent back from a distant probe answers old questions while giving birth to new ones. The silent, steady light of the planets and the distant stars continues to call to us, a timeless invitation to wonder, to explore, and to dream.